All right. Um, let's do some posters. Posters. Actually, most of these I got hang up in front of me right now, so that might be helpful. Some of these are realized you make large print posters, but here we go. Right, so unit 4, thinking energy, we're going to quantify that in joules, or you could say work. Right, work could be a transfer of energy as the same unit, joules. Right, and that breaks down into newtons times meters, and that further breaks down to kilogram meters squared per second squared. Right. Side thought. Do you guys remember when we got to December rotational mechanics, there was torque that was quantified in Newton meters that was not joules. So careful about that because that's a totally different concept from torque, right? Deceptively similar looking units, right? Okay, and there's also this concept of like a rate of energy or a rate of work, right? You could quantify that in watts, right? There's like a 40-watt light bulb, right? Okay, so something about passing 40 joules per second is what that means, okay? Right, for the break. Okay, right, so right there. I have two similar type posters. I don't know. You consolidate these or what, right? For forms of energy that you care about for this unit, right? So let's go ahead and switch to the next one here. Okay. So let's see, these are all in terms of variables, right? So work could be some kind of force times distance. Notice that's a dot product, so you care about like parallel components, right? Now, if you lift something for some height, you could say, well, there's a force times distance lifting it, right? That could be, mg times h, right? Weight times height, right? Gravitational potential energy, right? Right, the more universal form that negative g mm on r, right? Actually kind of applies to the FRQ we were just looking at, where some of the escape speed, you use this to drive that, right? If there's like a change in gravitational field, you might have to use this version of, right? I don't know if I've ever seen APA ask an exact application of this one though, so you guys probably are not going to see that as a question. Right? A little bit extra in it, right? Ooh, energy stored in spring. I mean, okay, like all these gold ones. You guys see some of these rose colored gold, right? You're gonna get those questions on the AP exam, right? Right. So energy stored in spring, which remember, this guys, this is different from force on a spring. What was force on a spring? F equals what? Kx, right? And then the energy stored is 1/2 kx squared, right? So different concept, different units, different application, right? Energy in motion, 1/2 mv squared, okay? And then we got to December rotational kinematic, or rotational dynamics. Here's like if there's a ball rolling on the floor or a disc rolling, or okay. All right. And then here to kind of rewind a little bit. Right, the units for all those would be joules, but power is measured in watts. Okay. Okay. And then watts as a unit is different from work as a variable. So about that too. Right. Right. Work is force times distance, and remember the dot product means parallel components. So okay, so you're pushing a shopping cart down and forward. Well, the shopping cart only moves forward, so you can only multiply together the parallel components forward, right? So that, okay, so if you have this angle between those two, that's the cosine theta, right? What if you're lifting something up some stairs? Okay, so you're moving it forward and lifting it, right? But the forward part doesn't actually require the force, but lifting it does. You have to lift against its weight, right? So only the up, okay. Now, careful that whatever angle you're giving, like here on this poster, I listed the angle as the angle between the vectors, so I can put it directly in the definition cosine theta, right? Careful you're not given like this other angle. If they give you this angle down here, that would not be the angle between the vectors. That'd be, well, because the complementary angle, this would turn to sine theta, right? Every once in a while you see something like that. Okay. Right. Ooh, you're gonna see force versus distance graphs, right? And then if you see force versus distance, but probably 90% of the time or more, the question is going to be about work, right? Energy transfer, okay? Something like that. It's just the area under that curve. Okay. Right. Closed and open systems. So here I've got energy conserved within a closed system, right? You can't create or destroy some number of joules. Okay? Now, if the system is open, there could be work done on the system or by the system. So you could have some kind of external force is one way to write it, right? And then therefore there could be energy entering or leaving that system, right? All right. This next one, because I wanted to have you guys some challenges here. See if you guys can solve this, right? Right. So here, what I got covered up. You guys got your notes out, right? You guys ready to write this in your notes? Right. So challenge question for you guys. Challenge question. See if you guys remember this. what if you want to figure out what's the maximum height you can throw a ball? Let's say you know how fast you can throw a ball. Right? So I know how fast I can throw a ball. Right? What's the maximum height it goes to? Which is really just an algebra shuffle away from a summer question. Let's say you throw a ball straight up. I remember on your midterm, I said, like, suppose you're next to a multi-story building and see what floor it goes up to, right? Can you sort of back calculate how fast you can throw it to get there, right? Really, both of those questions. Okay. So, okay, both those questions, I got two different approaches that I'm covering up on that poster. Right, so you guys writing that down? Okay. Yeah. Okay, just to save a little time, just pick your favorite method, either kinematic or energy, and see if you can derive them from scratch. Okay. How high does the ball go? Say, as a function of how fast did you throw it? How high does the ball go as a function of how fast you throw it? Okay. Of course, both those methods are going to lead to the same answer in the end, but it's really different looking approaches. Can you figure out either one from scratch?
So you're trying to find out how high?
Yeah, how high does it go? Yeah, so your final answer should say h equals. Okay. So yeah, suppose you know your throwing speed. And Nolan running this ball up at 100 miles an hour. So how fast is that? Or how high is it going to go? All right, you guys got the answer? How high it's going to go? Yep. All right. All right. What do you guys get? Who's got the answer? Who's got the answer? What you got, Nick? E squared over 2g. Boom. Exactly. Yeah. Your throwing speed squared divided by 2 times gravity field. Right. There's two different methods to do that. Look at the whole thing right here. So the old kinematic one way to do it, which could first get you to the right answer. So you say, hey, how about that third kinematic equation, right? The time independent one. Okay, so see, maximum height would be, well, I know at that point it's 0 speed, so I can plug in 0 for v final. The initial is my throwing speed. Okay. The acceleration, well, it's like g, but opposite of the way through it, so I'll throw in a negative, right? And that displacement, well, that would be the maximum height that would correspond with the 0 final speed, right? Do an algebra shuffle and boom, get exactly what Nathan said, boom, right there, right? And then right beneath this, to put the other question you could ask is like, oh, what is your throwing speed based on like how high does it go? Oh, and look at that, it's square root TGH, right? Which you guys have seen a lot of times in this class too. Right? All right, here's the energy approach. You say, well, energy is conserved. Down on the ground level, it had a bunch of kinetic energy just as it was leaving your hand. 1/2 mv squared. It went up to some maximum height. And at that maximum height, it's 100% potential energy, right? Gravitational potential energy, MGH, right? Now, this one, the mass is, remember, kinematic, we never dealt with mass. Right? This one, I see mass, but the mass cancels out. So you still get the same answer as with the kinematic approach. Right? And then same thing, you could ask the other question, how fast did you throw based on how high does it go? You get the same answer too. Okay. You guys got that? Ooh. All right. Here's one of my favorite setups. Suppose you got a block, you press it to a spring, squash the spring, compress the spring some distance x, and then let it go. Let's say there's no friction, so no frictional losses. Don't worry about that. Okay. And this loop has some height h. Hey, how fast is that going at the top? How fast? And if there was a little bit of friction, then you could say, well, kind of what would be asymptotically the maximum speed that it could get up to. Can you guys do a setup? Can you guys set up the equation that would answer that question? In your notes. Okay. What equation is going to solve that setup? All right, did you guys write this right here? Okay. So energy is conserved. Okay. It's a closed system because there's no friction. Okay. It's all the energy stored in the spring, initially 1/2 kx squared. Let's say it's like 100 joules. Okay. And the energy, by the time it gets to point B, remember all these conservation of energies, you're going from some point A to some point B. So up here at the top, right? Well, it had to be lifted against gravity. So there's MGH, has potential energy. It's also in motion. There's your 1/2 mv squared. So maybe if you start with 100 joules, maybe, for example, 30 joules go into lifting it that height, and the other 70 joules are left over to go into its motion. Like that. Ooh. pendulum maximum speed. Okay, is this, what am I? Oh, okay. Okay. So without looking at the answer that's hanging over my head, can you guys solve that one from scratch? You guys should be able to solve that one. Solve that from scratch. How fast? All right, so yeah, you guys are figuring out, got a mouse on a string. If there was a paragraph description, they would almost certainly say the string itself has negligible mass or some version of that. Right, so all the mass is in the above. Okay. Yeah, how fast are you swinging down here? Okay. Okay. So okay. Let's do a few steps at a time. Okay. So yeah, I would use conservation of energy. See, I see a height change and a speed change. You could use the kinematic to solve it, but I mean, we get you the right answer. I like this method better. Okay. Okay. So, do you guys have what kind of energy at the top here? MGH potential. What kind of energy at the bottom? Kinetic 1/2 mv squared. Right. Oh, MGH goes to 1/2 mv squared. Right. And it's equal because energy is conserved. Right. In gray ink, I put what if you like push off. Right. What if it's on the start press push off? And you also include that gray ink term. Okay. If not, if it starts from rest, then just put black. Right. Guys, good so far? Okay. If you're looking for this V, okay, so we're solving for that V, right? Okay. Now the last tricky part for this pendulum is, here's where you have to break out some geometry. Can you find this height change in terms of this angle and this length? Can you do that? Okay. You guys, another minute here. All right, here we go. Right, so, oh, okay. Let's say just did a bunch of substitutions right there. There you go. I'm thinking I see a nice triangle here. You guys see a right triangle? Ooh, right triangle. Right. So that this leg of this right triangle, will that be L cosine theta? You guys see L cosine theta? Right. Therefore, this height change is the difference between the full length and L cosine theta. So I can write that, L minus L cosine theta. Right. But if you like to, you could factor out an L. Right. AP won't count it against you if you don't, but I think it looks a little prettier. Right. And then you substitute that right there. Right. Because otherwise it's just square root 2gh, isn't it? Square root 2gh. But the h is L minus 1 minus cosine theta. Right? Okay. And then the last detail is, well, what about all this gray ink? What if you pushed off? Right? So a lot of times the first time students are learning this, back in when we were just September, October or something, right? Is November maybe, right? Is they'll want to say, oh, well, the speed at the bottom is the initial speed plus square root 2gh. Right? But that's no good. That gets you the wrong answer. Okay. Notice what you have to do. You have to do the square root of the push-off speed squared plus 2gh. Right? Which is going to give you a different answer. All right. You guys did a lab version of this. I had you guys calculate what should be, and then you use the speed gates and say, well, empirically, what is it? And it should have lined up. So, ooh, right. This one, okay. This one for sure you got to know, right? Galileo drops ball from Leaning Tower. What is the crash speed? Right above the ground. Okay. You guys plan. Let's see if you can drag out the graph. Okay. This one's pretty fundamental. Okay. This one's even more fundamental than the pendulum. Maybe we should have done this one earlier in that set.
What are we trying to find?
What's the crash speed? What's this V? Right? What's the crash speed? All right, so you guys said at the top it's all MGH, at the bottom it's all 1/2 mv squared. Okay. So energy is conserved, boink, right? And then rearrange it, you get square root 2gh, right? Right. So you guys go with Galileo. Yeah, can you see that more? It's poster hanging in front of me, so can you see that? Ooh, car brakes to a stop. Right. Now this one I'm going to treat as an open system. So maybe it's just a system consisting of only the car, or you'd say even the car or system, right? But either one of those defined systems, there'd be an external force from the road. This friction force from the road is acting as an external force for some distance. Okay, so therefore, open system, right? Okay. So all the other systems we looked at so far today have been closed systems. This one's an open system. Okay. Can you solve for the braking distance of the car? What is the braking distance of that car? Say in terms of its initial speed. It's the braking distance of that car as a function of its initial speed. All right. I have a pretty good guess what the next line is under this paper. What kind of energy does the car start with? Yeah, 1/2 mv squared, right? And when I say minus work by friction, ooh, I can write that as an expression too. That's what times what? Yeah, for this friction force times this braking distance, because that's what that's going to be, right? Oh, and what kind of mechanical energy when it's braked? Yeah, 0, right? Okay, so we go to 0. It's open system. There's no kinetic energy. It's not moving. There's no potential energy. Didn't roll up hills to get there, right? Which would have stopped it faster. It's a hey, that's exactly what that is. Like that. Right? 1/2 mv squared minus force and resistance is 0 joules. Okay. Now, ooh, that friction force. Right? Yeah. Okay. Now maybe we can skip back to unit 2 type and say that friction force is coefficient of friction times this normal force. This normal force is equivalent to this weight. They make a double substitution right there. You guys think? Right. See what this looks like. Okay, so I left kinetic energy right in place. And then in place of this friction force, I got the coefficient of friction times. And then in the place of normal force, I got mg. And that distance is still that distant. Okay. The last thing you do is solve for that d. Now you can get an expression for what's the braking distance of the car in terms of its initial speed. Right. The other variables that matter are what's the coefficient of friction between the tires of the road. You guys think if it was a rainy road versus like a wet road versus a dry road, make a difference, right? Okay. Like the larger the coefficient of friction, right? Because if you pump up the friction, what happens to the distance? It gets shorter and shorter. Okay.
Using the kinematic, I was also able to get a sequence.
Yeah. Okay. Yeah. Kinematic. You could do that third kinematic equation thing. Okay. Yeah. Yeah. True. Yeah. You could do kinematic. All right. And then for acceleration, that would be u times g is the acceleration, right? Yeah. So you could do that way. Yeah. All right. All right. Okay. And then yeah, I always emphasize this point too. It's like if you triple the speed of the car, what happens to the braking distance? Yeah, 9 times. Right. Ooh. Right. Power. That was like a rate of work, rate of energy, work per time, energy per time. Okay. And then there's a specific scenario. It's like, okay, what if you have an elevator? Now this elevator I'm showing at constant speed. How do I know this elevator is moving at constant speed? Yeah, equilibrium. Yeah, because this tension force pulling up is balanced with the weight of the elevator down. Yeah, so equilibrium. Right? If you're standing in that elevator, would it feel as if you were at rest? Yeah, it would feel physically identical to being at rest. Right? It's like moving at constant speed. Right? In fact, if it is moving, you don't even know which way it's moving if you're standing inside it. Right? As long as it's constant speed, you can't tell which way it's moving. Right? If it's constant speed. Right? Oh, so you can take power's work per time. You can rearrange it for this specific scenario in terms of the oh, so here could be the question, right? Suppose there's a motor at the top of this elevator shaft pulling it up at that constant speed. Right? How many watts is that motor at the top of the shaft pulling? Right? So in terms of what is the tension in that elevator cable and how fast is it pulling, you can answer that question. Can you guys take this power's work per time and rearrange it and get the power output for the motor at the top of the elevator shaft based on how hard is it pulling tension and how fast is it pulling V? Can you guys do that? I'm gonna get one question about this on the actual AP exam. I'm gonna guess you're gonna get probably one multiple choice question. And hey, maybe this is one that's gonna put you over the edge and get you to pass, or take you from a 3 to a 4. Ooh, that's a big two. All right. Did you guys say? Well, I know work is force times distance, so I could substitute that, right? Okay, that'd be a good middle step. And then, ooh, hey, you could rearrange it, you could group these variables together differently. Instead of the grouping the force and distance to give you work, right? You could, hey, guys, what is distance over time? Velocity, boom. Force and velocity, right? So you guys got that one? Right. Yeah, I bet you're going to get to use that one time on the AP exam. Yes. Ooh, roller coaster minimum height. So maybe there's a scenario you want to figure out what's the minimum height of the roller coaster so you can drop it and it guarantees gets around. Right? You guys saw a video where some guy dropped a bowling ball, which has the other extra complication that it's rolling for the bowling ball, but let's ignore that. Right? Say just say frictionless surface or little tiny wheels. Right? So this is like a two-part problem. One first part you had to figure out in this green box over here is, well, there is a minimum speed to get around, right? That's like a unit 3 type question. That's what we were doing last week, right? What's the minimum speed to go around a vertical loop for a roller coaster, right? So you say, well, at the top of the loop, you let this normal force approach 0, right? And therefore, okay, I actually kind of stopped at v squared, right? You guys remember, Chia, this it's the same question as you put water in a cup and on a string and wheel it around in a vertical loop. How fast it have to go at the top? It was square root GR. Guys remember that square root GR? Okay. Then you back up one more step. Say, okay, well, how high a hill did I have to drop it from the first place so that it could reach that speed? Right? And that's a conservation of energy question. Okay. Suppose a closed system, no frictional loss. Right? We got MGH. Right now, if I'm playing off this height, I'm considering the ground to be down here. Right? So the roller coaster was going maximum speed down here, right? And then it slowed down as it was working its way up the hill. And it worked up to a height of 2r. So there's the 2r there. Right? And it's got some speed left over. How much speed? Well, it better have at least with this much speed. Right? So that's going to substitute there. Right? Guess that? And then there's a bunch of algebra steps. Boom. Right? So you guys good? All right. Let's see that next. Ooh, Atwoods. You guys know you see Atwoods all over the place in physics. You're gonna see Atwoods on the final exam, right? And last few weeks we've been looking at Atwoods in terms of, well, what's maybe the acceleration of the system in general, the downward acceleration of the large block, what's the tension in the string, you could ask, right? Now with energy, there's a good opportunity to answer a different type question, which is what's the speed after some height change? Okay? Which again, you could solve with the old method. The old way of doing it is say, well, okay, first I'm going to solve for the acceleration based on the masses, and then I'm going to kick back to kinematic motion and say, like after some distance or some time, they could ask you, so after some distance, right, how fast is it moving? So you could answer it that way, right? Or you can get straight to the answer with conservation of energy. Guys, what's the conservation of energy setup? Conservation of energy setup. Can you guys write that in your notes? Right. So this is really a specific question you can answer with this method, which is how fast is each block moving after some height change? Okay. Notice I'm not saying that after some time interval, I'm saying a height change specifically, right? All these conservation of energy equations, you guys notice we haven't really been saying how much time is. Okay, so I don't care, 1, 2, 3 seconds.
What are we trying to find here?
Right. What is the speed of each block after some height change? Okay, see, it's moving some height change h. Okay. So the big one's moving down, the small one's moving up. Okay, some height change. How fast is it moving?
Yeah, and that's not the maximum height.
Oh yeah, okay. Yeah, it's not a maximum height, right? Because if you had a string that was like a kilometer long or something crazy, you could just keep speeding up. It would just keep speeding up until one of the blocks it slams into the ground into the pulley. Right? Yeah. Now, if there was like a maximum height change situation, I'd have to do something like throw a spring on it. Like if one of these was grounded in a spring that was like tied to the ground, it's like okay, well then there would be some kind of maximum height, and then it would like start oscillating, right? But yeah, that's not what speed asks here. It's just saying like for some arbitrary height change. Suppose that this box moves 1 meter, right? The large one goes down 1 meter, the small one moves up 1 meter. How fast is it moving at that particular arbitrary moment? Okay, you guys have the answer on your paper? Let's start going through step by step. So I'll give you guys the setup. Right? So conservation of energy. Right? Again, the hint for how you could use this method is I'm talking about a height change, not a time interval. Right? So, the fact that the large block can fall, that's sort of like supplying the energy, right? so MGH. Right? And I'm thinking that energy is going to go into 3 different places. What 3 different places did you guys write? Uh-huh. Exactly. Yeah. Right. So the large block falling has to do 3 things. It has to lift the small block. So there's some MGH of lifting the small block. Some of the energy went that way. Right. Like the more massive M1 is, right, the left energy is left to go over to the other 2 places, which is kinetic energy. Right. So at the end of this height motion, each block is in motion, has some kinetic energy. Right. So boom. That's just right there. Oh, okay. So it looks like the entire poster is just a setup. Right. So I don't actually have a final answer on this one, but it's just the setup I'm showing. Okay. There's like supply of energy and the demand for energy, right? Supply, demand, boom. Right. Guess that. Right. And then, all right. So while you guys are digesting that or finish write that your notes. Right. This H is this H. Right. One block is going down. The other block's coming up, but they're tied together with the same string, so they're going to be the same distance. Okay? And this V is this V, right? So yeah, the directions are different. One's going down, one's going up, but same speed. And for conservation of energy, it's a scalar value. You don't care about the directions of these things. Okay? All right. Here we go. Let's see what next. Ooh. Yeah. How about this modified outward setup? You guys had a textbook question that was really similar to this one. Okay, so it's got crazy like 3 block outlet setup. Right? One of them's horizontal, 2 are vertical. Right? And ooh, maybe you can even throw some friction in for fun. Okay, so this one looks pretty encompassing. Right? So I'm going to treat this as an open system specifically because of this friction force. Right? Maybe this friction force is external to like the 3 blocks and the Earth system. So 3 block Earth system. Right? Or some version of that. Okay. So, yeah, maybe I need to reword this. I guess based on what you just said, it's external force. Right. So, the fact that the large block can fall, that's like supplying the energy. Hey, just like the last poster. Right. Now, treating this as an open system, I want to subtract off this friction force times some sliding distance. Right. And I left off some forces. It's like the weight of this one, the normal force. Okay. I help you figure out what this friction force is in the first place. Right? Okay. And then after that, what do you have left over? Okay, well, I need to lift this block, the small block, and then give each of these blocks kinetic energy. Okay, guys see all that? Okay. I also see this D, this distance it slides is equal to this height change for these 2 vertical moving blocks. Be the same, right? Okay, so that can help you, right? Because that D and that H is the same. Right? Static. And also this V and this V and this V, they're all the same speed because they're all tied together on the same string. Right. What next? Ooh, simple machines. Right. So here's different ways you get mechanical advantage. Right. Okay. So about you guys remember doing pulley systems? Pulley system. Right. Ooh, I got it. One rigged up right here. Right. Right. So the guiding principle here is that, see, if energy is conserved, you can't create or destroy energy. So your input work can match your output work at best, right? If there's no frictional losses or anything with that, right? So, so with a small force pulling a large distance, you can lift a large force, but only a little bit at a time. Right. Mechanical advantage. You got ideal mechanical advantage, actual mechanical advantage. So the ideal is just based on the geometry. You say, well, how far did it pull versus how hard did it lift? Right. So that's a geometry question. So it's just like 3 to 1, right? I guess the 1, 2, 3 strings 1, right? It's supposed to weight 3 ways. Right? The actual mechanical advantage is, well, what if you actually test this out empirically? Right? And it's probably going to be a little bit of a lossy process, right? Maybe there's a little frictional loss. Maybe if these strings aren't exactly vertical, there's a trigonometry aspect. You have to pull a little bit harder than you would, right? So I'm showing 3 to 1, but maybe you try this out and maybe this weighs 1 Newton and you have to pull with like 3.5 Newtons of force. Okay, so you have to pull with an even greater force. Okay. Wait, I said that backwards. Sorry, maybe this is 3 Newtons and you should only pull with 1 Newton. Right? But maybe you pull with like 1.5 Newtons, right? So it's not as good as would the other way. Right? you guys did this lab. There's other ways you can get mechanical advantage, right? Got a lever system there. Got a incline system. Suppose you got right luggage on wheels, and you're like wheeling it up an incline. Got this wheel system you could do. Right. Okay. And last bit, okay, AP's not gonna ask about this one, but okay. It's good to know extra. I think I heard a rumor that might bring this in starting next year. Right? So I guess if you guys are competing with next year students, then you guys might want to know universal gravitation. So, okay. All right. This is how does universal gravitation potential energy from a universal point of view, right? It's very simplified at MGH for say negligible change in gravity field. MGH, okay. For this class, this exam, you guys just know MGH for potential energy. Right? All right. Okay, so I do want to look at some of these right for the bell here. Okay. Guys, tomorrow I want to give you guys a multiple choice in class with AP Classroom. Can you guys bring your laptops tomorrow? Okay. Okay. And then so I'll open up that tomorrow morning, and then go over the solutions Thursday is the plan. Okay. If you guys remember, you might still have this page. You guys remember this 12-row energy table? It's like over 3 pages. It got all these different scenarios. Right? So some of these we're just looking at, like a poster for Galileo dropping the ball, right? Or the car breaking to a stop. Said tree is an open system, right? So what was the energy at point A, point B, and they can you solve for, right? And just to have a universal question, what was the speed of point B right there, right? So we're gonna find a pretty good one. We have that. Oh, yeah. I know which one I want to do with you guys. Okay. This bungee cord here, right? I asked you guys one on the midterm that was really similar to this one. And this, I think it was probably the most missed question. Right, so let's look at this one. Suppose you got like a bridge, and there's this bungee jumper, right? And here's like the river below. He's gonna, well, he's on a bungee cord, so he's all right. Okay, so there he is, bungeeing. And the scenario I gave you guys was, I told you the height of the bridge above the water. Right. Here, let's just do this in terms of variables. Right. I told you the unstretched length of the bungee cord L. Right. But also, I just told you guys the mass of this guy. Right. He's in a gravity field. Right. When it stretched, I said it stretches all the way until he just reaches the top of the water. You can touch the water and then it retracts. So I can call the stretch distance X. But that's really the same thing as H minus L. You guys see that? So I can do that substitution later. Right. Let's do a conservation of energy. Sum of energy at the top, so the bridge, equals the sum of energy when he's just touching the water. So at the bottom where he's just touching the water, right? So guys, what kind of energy at the top of the bridge? MGH, right? And then when he's just touching the water top surface, what kind of energy? Yeah, 1/2 kx squared. 1/2 kx squared. Except instead of k, I'm gonna say H minus L. And then, okay, don't forget to square that. Right? And the question I asked you was, for that exact scenario to play out, what would have to be the spring constant in that bungee cord? Right? If you thought of it being like a spring. Right? So I gave you the guy's mass. You can know gravity field is about 10 meters per second squared. I gave you the, I should change this to capital H, right? This height of the bridge above the water, right, which also shows up there. And I gave you the unstretched length of the bungee cord, so you could solve for K. I guess it'll work out like 2 mgh all divided by H minus L squared, like that. Okay, just like that. Okay. All right. Yeah. All right. So before you take off today, yeah, remember, make sure you turned your Unit 3 quiz into the gray tray. And if you score that FRQ with the asteroid, toss that in the gray tray, then I'll give you guys some points for that too.